Hey guys, welcome back. So we're looking at 2.5 today, powerful tens. So let's go ahead and jump right in. All right, so we're comparing graphs of the exponential and logarithmic functions. The graphs of f of x equals 10 to the power of x and g of x equals log x are shown in the same coordinate plane. Make a list of characteristics of each function. So for number one, f of x equals 10 to the power of x. What do we know about this? Well, if we look at it, is it increasing or is it decreasing? It's increasing. What else do we know about it? What about its domain? Do we know anything about its domain? Should be all real numbers. So domain, all real numbers. We also know that it's range. So when we have an exponential function, it usually has a value that it gets close to, but it never actually crosses. In this case, notice as we come down this way, so in the negative values, it's getting closer and closer to the x-axis. It's never actually going to reach the x-axis. It'll get infinitely close, but it will never reach it. So our range is going to be from 0 to infinity because we're never actually going to go lower than 0. So range is from 0 to infinity. All right, we have a y-intercept at 1. So y-intercept at 0, 1. And we have no x-intercept. So that's what we know about our exponential function. Now, our logarithmic function, it's also increasing. So notice we are going up slowly, but we are going up. So it's also increasing. Our domain for this is limited. We don't actually have any negative values in this case. Notice it's coming down along the y-axis and it's never crossing it. So our domain is from 0 to positive infinity. But our range, so these are reverse of each other. So the domain on the exponential was all real numbers, whereas the range was from 0 to infinity. Now on the logarithmic, the domain is from 0 to infinity, and the range is all real numbers. Now for this one, we do not have a y-intercept. It's never going to actually cross the y-axis, so there is no y-intercept. So no y-intercept. But x-intercept at 1, 0. So very similar functions and yet very different. So they are related, but they have some reversed qualities in this. So these are their characteristics. Like I said, they're similar, but they are differing. Okay, the next part. Each equation below refers to the graph of the functions f of x equals 10 to the power of x and g of x equals log base 10 of x. State whether they are true or false. If they're false, correct the statement so that it's true. Every graph of the form g of x equals log base 10 of x will contain the point 1, 0. This is true. It's always going to be true no matter what. It will never change. It's always going to have that x-intercept. Number 4, both graphs have vertical asymptotes. So an asymptote is a line that the graph approaches but never actually crosses. So with our exponential function, it was approaching the x-axis, whereas our logarithmic was approaching the y-axis. So one of them is approaching a horizontal, the other one is approaching a vertical. So for this one, it's not both graphs. This is false. It's not both graphs. It's g of x equals log base 10 of x. So that's what you guys are doing on this section. So you're going to be looking at stating whether they're true or false. And if they are false, yes, you need to take and fix those. So state what it should be, okay? All right, the next section is solving logarithmic equations, base 10 by taking the log of each side. So evaluate logarithms, evaluating the following logarithms. So we have log base 10 of 10. Sorry, lost my marker. So when we have a log base in the number, the actual number, so note this is log base 10. We never actually include the 10 because that's just the standard form of it. But when this number and our big number are the same, our answer is what the exponent is. Well, this one doesn't have an exponent, but all numbers have an exponent. It's 1. So our answer for this one is 1. So what about log base 10 of 10 to the 75th power? It's going to be 75. Once again, it's just the exponent. As long as the base number and the, it only works when the base of the logarithm matches the base for the exponent. So log base 11 of 11 to the 37th is 37. Log base m of m to the 9th, they're the same, so it's n. So it's all about your exponents. That's what's going to be your answer, is the exponents. Okay, the next section, solve the equations by inserting log base n on both sides of the equation. You will need a calculator. So for these, if you have an iPhone, this is how you'll take and do it. If you don't have an iPhone, hopefully it'll work in a similar manner. But here's our first problem. We have 10 to the n equals 4.305. What you want to do is in your calculator, if you have an iPhone, because I have an iPhone, so I know how it works on the iPhone, you're going to type in the number, so the 4.305, and then turn your phone to the side for that extended calculator, and then you want to look for the log base 10 button. You'll press that, and when you do, you get a really long decimal, but we're going to round it because it wants our answers. Well, it doesn't say where to round it to, but we're going to have a rounded answer, and what we get is 0.634. It was 0.6339, I believe, and so then it rounds it up to 4 there. So this is our answer. Now on 19, same thing. You're going to take the 14,521, and I will show you if I can find my phone. So we're going to type it in, 14,521, and then we turn the phone to the side, and then you're going to press that log 10 button, and you're going to end up with really big long decimal, 4.1619, yada, 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 yada. And the log base 10 button is, if I can get it close enough, this one right here next to the 4 when you extend your calculator, okay? So that's the button we want to use. If you don't have an iPhone, if you have an extended calculator though, just look for the log. It may just say log and then parentheses. It may not have the base 10 since that's our standard base for logarithms is base 10. So it might just say log with a parenthesis. If it does, that's what you want to use. If it's got the log base with the 10 actually wrote out, that's what you're using. You might have to test it out to see whether you need to type it in before or afterwards, because sometimes with some phones you hit that first, then you type in what goes inside the parentheses. Other times it's the reverse. So test it out on the ones that I'm doing now to see if you get the same answer, to double check which way it needs to be, because I don't know for all phones how you would take and do it on an actual calculator. It also would just depend on the calculator. So calculators, phone calculators, they all have different ways to take and do them. So like I said, test it out with these two to make sure that you get the exact same answer. And then, you'll know which way you need to take and do it. So for this one, it was 4.162. Okay. All right. The last section of what we're looking at today is about interest. So we're looking at compound interest. The formula for compound interest: if P dollars is deposited in an account paying an annual rate of interest R, compounded, paid in n times per year, the account will contain A equals P times the quantity 1 plus R divided by n to the n times T x power dollars after T years. I know it's a lot of variables in there, but the A represents how much money you have in the account. P represents the principal or what you started with. The 1 will always be 1. Plus, the R represents your rate. That's going to be the percentage that you're earning interest-wise. The N represents the number of times compounded. So typical ways of compounding, you could have annually. So once a year, if it's annually, you just use 1. If it's semi-annually, that means it's happening twice a year. If it's quarterly, then there's 4 quarters to a year. And if it's daily, well, then you're using 365, just like it says here. There's 365 days a year. And then the exponent, you'll use whatever you used in the denominator here, and then times how many years it's going to be in there for. So these are some very real-life situations. So when you're taking and looking to invest your money in different savings accounts or money markets, different things like that, being able to calculate and test to see, okay, how is this going to affect it? What should I start my amount with? You know, how many times should it be compounded if that's something you have a choice on, and for how long you should keep it in there to get a desired amount. I personally have used this a lot when I was looking into how much I should invest in savings accounts and looking at the different rates and how that affects the amount of money that's in there, and looking at, okay, if I start with this much money, what's it going to be after a year? What's it going to be after this much time? But what if I start with this amount? Will that make it grow faster? Will it make it grow less? So this is something that can come in handy when you're taking and testing this out, rather than having to, you know, have someone else do it for you. Being able to do this for yourself is a good thing. Okay, so for 21, it says how much money will there be in account at the end of 10 years if $3,000 is deposited at 6% annual interest compounded as follows. Now, I'm going to tell you right now, 6% is amazing. 6% does not happen. I don't know where they're banking, but I wish I was banking there. A lot of the percents nowadays aren't very high. I will tell you currently I have 3 different savings accounts. One is getting 1% interest. Another one is getting 0.1% interest. And my third one is getting 0.05% interest. So they're not very high interest rates. So this is a very high interest rate. So it's a really good interest rate, quite frankly. It may not seem like a lot, but it is. Okay, so based on our equation, let's set up what it should look like based on our information. So A equals, P was our principal or starting value, so that's the 3,000. Oops, I need more space for this. So A equals 3,000 times 1, that's going to stay the same, plus, now, anytime we're dealing with a rate, we don't actually want to put the 6% there. The rate we need to convert to a decimal, so we move the decimal place twice. So this is going to be 0.06. So I'm going to put 0.06 over the number of times it's being compounded. So that's going to change for each of these problems. So for right now, I'm going to leave that as an n to the n times, we want our t value, so our time in years. So all of these are in terms of years. So that is 10 years that we're looking at here. So I'm going to rearrange that just for calculation purposes. So this is our formula right here. Now for A, B, C, and D, the only thing we have to change is this n value right here. So if we're doing this annually, the n value is going to be 1. So we're going to have A equals 3,000 times 1 plus 0.06 over 1 to the 10 times 1. Well, 0.06 divided by 1 is 0.06, plus 1 is 1.06 to the power of 10. Now, this is where you plug it into a calculator. And quite frankly, you could plug it in a calculator right here. My suggestion